Hello, my name's John Perham, and in this little series of talks I'm going to tell you something about the mathematics behind the perspective transformation. And the reason I've chosen this example is that I want to illustrate the use of a computer algebra system, Mathematica, a screen capture software, in this case Windows Media Encoder, and a Wacom pressure-sensitive tablet and pen, and that can be used to annotate the screen picture. So let's get a pen, and now I can write on the screen picture to illustrate some point, for example. So let's get rid of that. And we'll use it when we need it, if we need it. So let's get the mouse pointer back again, and now we've got that. So I want to use that to produce interactive learning material in the form of Mathematica notebooks and annotated video lectures in the form of compressed video files. And I've also used a microphone headset to improve the quality of the sound. Making this using my laptop computer. So the physical model on which the perspective transformation is based is the pinhole camera. But let's say a little bit about perspective. So because if we look at a photograph or a painting, the planar image has a pseudo three-dimensional nature due to the geometry of how it was formed. And artists have instinctively used the perspective transformation for many centuries, almost certainly without any knowledge of the three-dimensional geometry describing how the image is formed. So this project introduces many concepts from three-dimensional vector analysis within the context of a real application, including spherical coordinates, the parametric representation of lines and planes, Gram-Schmidt orthogonalization, subspaces and projections, and all these pieces of knowledge are needed to produce a realistic two-dimensional image of, for example, a wireframe pyramid, which is what we're going to try and do. So let's get started and look at modeling the pinhole camera. So here's a diagram of a pinhole camera which we're going to generate in a minute. And the way a pinhole camera works is that we have this green line, which is a line from the object, a point on the object being photographed or filmed, which is passes through the pinhole, which is this green blob here, and strikes the focal plane here to form a negative image. And the way we get the positive image is to produce that ray backwards until it strikes this red square, or the plane containing this red square, which is called the screen or image plane, and that plane is parallel to the focal plane and the same distance as it from the pinhole. And so this, and we can see that this image is kind of three-dimensional, especially by, if we rotate it around, we can see that how it changes. Okay. So let's get on with modeling it. Well, the first thing we need to do to draw this picture, or this diagram, is to define the 4 points at the corners of the two squares, which are defined, their coordinates are defined in this list here, which I've called vertices. And this is a piece of Mathematica code, and I can execute it so that now vertices contains, the name vertices contains the coordinates of these points. And now I want to define the 2 points on the at the ends of the green line. So the first one will be x minus 1 and z, which will be the coordinates of the point in the focal plane, and u1 and w will be the coordinates of the point in the image or screen plane. And keeping these general because what I want to do is for x and z to be able to compute the corresponding values of u and w. So let's write down the, or let's generate the, well, we better generate these points first, and we'll now generate the parametric equation of the line joining them, which will start at the first point and proceed a relative distance t along the line joining those 2 points. So t is the parameter. And if we look at the components of this vector, we can see that the middle or y component is 0 when t is a half. So we can find where that, or we can find the value for, or equations for the value of u and w by requiring that that is the origin of coordinates, in other words, the pinhole. So we do that, and we see we get 2 equations. So u is defined in terms of x, these are the left-hand sides of the equations, and w in terms of z. So we calculate those, and that's what the answer we get, which is not surprising. In other words, if this is the point minus x minus y, then this is the point plus x plus y. And we can now, to visualize the whole thing, we need to find numerical values for those points. So I've just taken the point minus a half in the focal plane, and then generated the numerical values of the endpoints. And now, to generate that picture, I now execute this piece of Mathematica graphics code, which will draw all those bits and pieces. And there we have it. You see, we get this picture, which has this 3-dimensional feel to it. You can see that the 2 planes in the image aren't quite parallel, and that is one of the aspects which gives it its 3-dimensional character. So let's pause the show, and because we don't want the video files to be too big.